So in this lesson, we're going to try to understand the fundamental theorem of calculus part 1. We know that fundamental theorem of calculus part 2 and part 1. And the part 2, we have seen, how it works, right? And of course, we're gonna see more of it. And part 1 is the part that is a little bit difficult to understand. So this section, in this lesson, the title would be Understanding the Fundamental Theorem of Calculus Part 1. And in another recording, we'll be proving, we'll have a proof of Fundamental Theorem of Calculus Part 1. But we're going to place the understanding of this Part 1 first. Fundamental Theorem of Calculus Part 1 has the following statement. It says, if f is continuous on a closed interval, then g is defined. Okay, so g is a function that is defined as the integration, a definite integral between a to x. Okay, so please notice, so let me make the font a bit larger. Please notice g of x, right, is defined as a function of x. And this x is the upper limit of the definitive, is the definite integral. And so we're going to have to consider the meaning of a definite integral. So when we integrate for any fixed x, and this x will be fixed, and we'll be doing the integration, and we get a quantity, and this quantity will be dependent on x. And Fundamental Theorem of Calculus Part 1 states that g, which is defined as such, is continuous on the closed interval from a to b and differentiable in the open interval a to b. And what is more, the derivative of g with respect to x is f of x, right? We saw f of t. So they're the same function, except that here is f of x. Okay, so what does this mean? This means that g is an antiderivative of f, right? By definition of antiderivative. So that's tell us another piece of information. So let's try to understand this. Okay, so I'm gonna use a couple of examples. The first example I chose is that I chose f of x is a constant. Okay, f of x is a constant. If f of x is a constant and we write it as f of t, that will also be a constant. And really, these two functions, x, t, they're just placeholders, right? They represent input, output. They represent input x, input t. Really, there's little difference, except that when we are doing the integration, we don't want to use x here to avoid the confusion, okay? All right, so f of x. I'm going to remove that for the moment. What is f of x? We know f of x is a constant, right? This function is a constant function, so we draw this picture. So it's a horizontal line. This is a horizontal line. So f of x is this line, and this is the rectangular system. A is any constant. A is any constant. I choose A to be here. A can be here, could be there, any constant. But A is a fixed number. A is a fixed number. So in our consideration, is A to B. So suppose this is A and B is somewhere here, right? So B is somewhere here. So X is in between. So when we consider g of x, right? So we consider g of x defined as such, because f of t, right? F of t, I just deleted f of t, but f of t would also be 1 as well, right? So for this particular g, It's also a constant, so this is a 1, right? So this will be 1, okay? So a to x, from a to x, integrating f of t, which is 1, is the area underneath the curve. And of course, here we don't have a curve. We have a, so this is the area. Okay, this is what a g of x. You can see g of x, right? You imagine x is move is if x for this x value, the area is this much. If x moved over here, right? If x moved over, so if x is moving from, if x, if I imagine this x moved, if x was here, this will be the area, right? So that would be the rectangle. And if x is here, so you can see as x changes, the area would be different. So suppose that I have a, so here I have an x here, right? So this is g of x, and that's the area. That's the area underneath the curve. The curve happened to be a straight line. If I have another x, right? So I'm going to make it a star. If x is shifted here, and then the area underneath the curve will be more, right? Will be more. So what this means is that g of x is a function that is dependent on x. All right, so I'm going to write it down. So g is a function of x. Of course, that's why this explains why we use that notation. Okay, so this is g of x. So let's see the variation of g of x, right? Just for this particular function, for f of t, right? So if g of 1, right, on x equals to 1, then the upper limit of the derivative will be 1. So this is 1, so we take a derivative, we take integration, which is the area underneath the curve. We know how to do that, right? So this is the second part of a fundamental theorem of part 1. This is fundamental theorem of calculus part 2 being applied here. So it's 1 minus a, right? A is a constant. So g of 2 is, x will be replaced by 2, right? G of 2, x will be replaced by 2, right? We integrate it, we get 2 minus a. 2.7, right? So g of x, for this particular function, g of x, then this x is the same as the x up here. Then we apply fundamental theorem of calculus part 2, we will get g of x. In this case, it will be x minus a. Now, with g of x equals to x minus a, and then we take a derivative of g, what do we get? G of x equals to x minus a. When we take a derivative, and we got 1, because the derivative of x is 1, the derivative of a is 0, a is a constant, so that is f of x. So fundamental theorem of calculus part 1 is illustrated in this case as the derivative of g is equal to f. That's what it is. You can see it is true indeed. right? It is true indeed. And let's look at the second example. Let's look at the second example. This time I choose f of x equals to x squared. And of course, f of t is t squared. It's basically the same function. So we integrate it from a to x and define this integral, definite integral, as g of x. Obviously, the area underneath the curve is dependent on the upper limit, as the lower limit a is fixed, right? So when we integrate this for x, right, g of x, as we integrate it with respect to t, so we're finding the area between a to x, and that is the total area, right? That's the total area right here. So we're adding, so we're finding this area underneath the curve. And of course, x could vary, right? So now for this particular x, the area is going to be 1/3 of x raised to the power 3 minus a to the power 3, applying fundamental theorem of calculus part 2, right? So what if we take a derivative of g of x in this case? So you may like to grab your paper pencil to find the derivative. Okay, to find the derivative of the g here. This is the g, when f equals to x squared. And we got g to be 1/3 of x raised to the power 3 minus a to the power 3. So when we take a derivative of g, and that's going to be 1/3, and the derivative of x to the power 3 is 3 times x squared. So we got x squared. Whoops, we got, wait, I'm sorry. This is going to be x squared. So once again, we have demonstrated. But this, even though this is not a proof, these are verifications to help us to understand the fundamental theorem of calculus part one, okay? Let's look at another example. And this example I've chosen is f of x is a sine of x, right? So this is the sine curve, right? So the area, the area between a to x, a is arbitrarily chosen. I just choose a to be here. So between a to x, right? Suppose b is somewhere here, right? So x is between a and b. So between a to x, this integration will give us the area, okay? Will be the area. This area, of course, is negative, and this area, the sum of these two areas. And so that's the meaning. And fortunately, we can calculate, because we know the antiderivative of sine theta is negative cosine theta. So we plug it in, right? Applying fundamental theorem of calculus part 2, and then we take a derivative of it, right? We take a derivative of it, and then we take a derivative of g, right? And the derivative of cosine is a negative sign. So that's how we get sine x. So once again, in this case, g prime is f of x. One more time. There are many, many such examples. But all of these examples is actually, we have the ideal case that we can easily integrate. We can easily find what a g is, but sometimes we don't know what it is, or sometimes it's more difficult to find what a g is. For example, okay, so let me give you another example. for example, I have an f here, f of x, okay, is going to be equal to root of 1 plus x raised to the power of 3. Okay? If I define g, and g is equal to the integration a upper limit x, right? I'm going to do f of t dt. Okay? In other words, we're going to plug in f of t, and that is going to be root. In this case, to find the antiderivative of a root of 1 plus x raised to the power 3, I'm sorry, this is bt, it's actually pretty difficult. It's actually pretty difficult. At least for now, we, in our current method, our current, situation, we cannot find it easily. As we learn more new methods, we'll deal with it. However, we know that this is a function, g is a function that dependent on x, right? And the g is dependent on the result of this integration. So if we plug in if we make a picture, right? This picture, okay? So this is the graph of the function, right? This is the graph of the function. So if we are, so let me, suppose I choose an A here, okay? I'm going to choose an A here, right? This is RA. This is RA, right? And there's another place I'm going to choose it to be X, right? So another point, which is X. And of course, B is somewhere here. B is somewhere here. And integration from A to X would be the area. Okay, it would be the area underneath the curve between A and X. Okay, so this integration will give us the area. Okay, this much is the area underneath the curve. That's the meaning of it. Although we cannot find what a G is, right? And although we cannot find what a G is, but we can, the fundamental theorem of calculus part 1 can tell us what a G prime is. Okay, what is the derivative of G is? And the derivative of G, okay, so let me bring this one over here. Okay, because otherwise the picture, okay. So even though we cannot find what a G is exactly, but we can find out by fundamental theorem of calculus part 1, we know the derivative of G is f of x. i.e. that G is the antiderivative of f of x. It shows that it exists. It shows that it exists. Okay, so this is the fundamental theorem of calculus part 1. And there are some other situations. For example, right? So let's go back to the fundamental theorem of calculus part 1. Okay, so I'm going to bring this information. Actually, I'm just going to do it here, right? So g of x, we can define g of x like this, but we can also define g, right? G of suppose I'm going to do some composition, right? So we're going to see some composition situation, composition. So we know that g of x is such, right? Suppose I'm going to do g of x raised to the power of 2. According to this definition, right? So this is the composition of g with x squared. So that's going to be, that's going to give us that. So this is going to be x squared. You see what I mean? So g of x squared. Since we know the derivative of g of x defined as such, we can also apply chain rule to find the derivative, okay, to derivative of g of x squared. How do we do that? How do we do that? Right, this is what we can do. Applying chain rule. Okay, so we have derivative du. We're gonna have g of u, right? And then du dx. And we know that u is x squared. U is x squared. So what is gu? What is g of u? G of u, right? The derivative with respect to u. G of u. This is g of x, right? This is g of x. So g of u, this will be u, right? So g of u is such. So we're taking derivative of g of u with respect to u. Okay, so that's one part. And the other part is dx squared dx. That's going to be just 2x, 2 times x. But how about this part? How about this part? This part we can do, but this is basically g, according to Fundamental Theorem of Calculus Part 1, the derivative of g, derivative of x equals to what? Equals to f of x, right? Now, what if this is u? Well, this is be f of u, right? So with that, and this is taking this part is basically the derivative of u. This is a gu. Remember, we just did a little substitution here, right? So this part is going to be equals to f of u. F of u. Okay. So we can also work out combining Fundamental Theorem of Calculus Part 1 with chain rule to take a derivative of a more complex functions. So in this case, I think we're just going to do with this one example here, and we're going to have another video to show you some more examples. Thank you for watching. Until next time.